Okay, so like I said, we're interested in solving the heat equation. We are going to be solving a very specific form of the heat equation. So again, a heat equation is just a boundary value problem. The one-dimensional heat equation that I gave you was some constant K multiplied by the second partial of U with respect to X is equal to the partial of U with respect to T. And then a few things to remember. K is going to be positive. X, which represents the spatial dimension for the rod, the length of the rod is going to be L. And then time is always going to be positive. Now, we talked about you need to specify the boundaries. So what's happening at the end of both rods. And then you're going to need to specify the initial condition. So here are our two boundary conditions. U of 0t equals 0 and U of LT equals 0. What are those boundaries telling us? Temperature at both ends is held at 0. Then we also need to specify what's happening at the beginning. So we have U of x0 equals f of x. This is telling us at time 0, so the initial temperature when time is 0 is f of x. Now, sometimes you're going to know what K is, sometimes you'll know what L is, sometimes you're going to have a specific function for f of x. A few things to know. What makes this homogeneous is these zeros right here. So we're going to be solving with zeros right there. Another thing to know is that this notation here for the equation is pretty tedious. So sometimes you're also going to see the equation written like this. Same equation, just written in a different manner. Okay, so this is a partial differential equation, which we've talked about is pretty complicated to solve. What is the only way we know how to solve these? Separation. So let's try that. So we are looking for U of xt. And we're going to start out by assuming that our U is the product of a function of x and a function of t. So we're going to have big X is a function of x, and then big T is a function of little t. I'm going to number these equations because we're going to, or these, the equation and the conditions, because we're going to need all of those at a certain point in time. So if we use our U of xt and we plug it into this first equation here, we're going to get K times x double prime t equals x t prime. And again, remember I'm dropping the little x. So this is not a variable x. This represents a function. So if I separate, I'm going to get x double prime over x. I'm going to move the k over to keep it with the t. So this will be t prime over kt equals negative lambda. This gives us two equations, one in terms of x and one in terms of t. So the equation in terms of x is going to be x double prime add lambda times x equals 0. One in terms of t will be t prime add k lambda times big T equals 0. Okay. For which of these equations, the first one or the second one, do we need to consider all three cases? First one. Do we need to consider multiple cases here? No. Okay, so we're going to start with the left equation because it's the more complicated one, and we're going to look for the three different cases. First case being lambda equals 0. Now, do you guys remember going through all these various cases and solving them? Okay, I don't want to be repetitive, so it's okay if we don't go through and solve again. Rachel?
Yes, but how do you know which one has multiple cases?
If it has a second derivative, that's where you're going to have to consider the different cases. Okay, so in the case where lambda equals 0, we get big X of little x equals C1 plus C2 little x. If that lambda equals negative alpha squared, so if lambda is negative, The solution we get is C1e to the negative alpha x plus C2e to the alpha x. And then in our case where lambda is positive, we get C1 cosine alpha x plus C2 sine of alpha x. Now, we are not interested in all three cases. We want to know which of these cases are going to give us non-trivial solutions when we look at the conditions above. So far we only looked at the main equation. We didn't look at the boundaries, which were the two conditions listed under 2. And under 3, we didn't look at the initial value yet. So now we are going to go to those two boundary conditions that we wrote above. So first we wrote that u of 0t is equal to 0. This means put in a 0 for x. So that would be x of 0 and t of t. And then we said that u of lt is equal to 0. That would be x of l times t of t. Okay, with me so far? So we have a few different possibilities here then. If this product has to be 0, that gives me either two cases. X of 0 is 0, or t of t is 0. Which one do you think I'm interested in? X being 0 or t being 0? What happens if this is 0? Trivial, right? Then we're going to be 0 for all values of t. Okay, so we don't want t of t to be 0, because that would give us trivial solutions. That then tells us that x of 0 is equal to 0, and big X of L is also equal to 0. So now we go back to the three cases. Okay, first case where lambda equals 0. If I substitute in x of 0 equals 0 and x of L equals 0, do you guys trust that I did that correctly? Like, is it okay if we don't go through the actual substitution?
Yes.
Okay, I don't think we know what I'm talking about. If I go back here and I plug in 0, 0, that's going to give me a C1 of 0. If I plug in x of L equals 0, that's going to give me C2 equals 0. I'm going to end up with x equals 0. So ultimately, I'll end up with u equals 0. Guys, why are we looking at me like we have no idea what I'm doing? It's a boundary value problem. Are you comfortable plugging these 2 points in to find C1 and C2? That's what I'm asking you. Okay, going with the majority here. If you're not, we'll figure it out later.
Oh, you just mean like plugging in 0 for x, for little x, and
Yeah.
plugging in 0 for big x too?
Yeah.
Oh.
And then in this case, this is little x, that's big X. Solving for C1 and C2. Everybody with me now together? Okay, so we're okay if I don't actually do that for all three cases and I just show you what the result ends up being. Okay, this will always be the case. So what I'm telling you is that this case here, we are not interested in because we end up with this trivial solution. If we look at lambda being negative, this again will give me big X of little x equals 0 and u equals 0. You can go through that yourself. But what this is telling us is these two cases we don't care about. We don't have to consider. The only one that we really care about is when lambda is positive. If lambda is positive, if I plug in x of 0 equals 0, this will be 0, this will be 0, C1 then will have to be 0. So this gives me C1 equals 0. We also know that x of L equals 0. So that'll be C2 sine of alpha times L has to equal 0. Okay, then do you guys remember doing this before? We said we don't want C2 to be 0 because we already got C1 to be 0. That'll be trivial. So then we said we really want this sign to be 0. So we said that sine is 0 at n times pi, if n is any integer. So we got our alpha to be n pi over L, when n is 1, 2, etc. Does that look familiar?
Yeah.
Okay, good. It should. So here's what that tells us. We have non-trivial solutions. When that lambda, which again is alpha squared, is going to be n squared pi squared over L squared, for n is 1, 2, 3, etc. Why did I start n at 1 and not at 0? We don't want lambda equals 0. We already showed that that's going to give us a trivial solution. These were called the eigenvalues before. We then would plug the eigenvalue into the function, which in this case is big X, to get our eigenfunctions. So big X will be C2 sine of n pi over Lx, again when n is 1, 2, 3. Because we have sine of alpha times L. Okay. Now we have to solve the t equation. So we solved the x one, now we're on to t.
And this is applicable for all homogeneous functions or equations?
Not all. I'm going to show you later. This process is, yes.
Oh.
Yes, the process is going to work. Okay. So now we got to go back to our second equation. That was the t prime plus k lambda times big T equals 0. So this is separable. You're going to get t on one side, get everything else on the other side. When you do that, you get t prime over big T equals negative k times lambda. Integrating with respect to t, to little t that is. So we get natural log of big T equals negative k lambda little t plus c. Applying e to everything, we get big T is c3 e to the negative k lambda t. Now we know what lambda is. We know what the eigenvalue is. That was defined up above. So ultimately we get t to be c3 e to the negative k n squared pi squared over L squared times t. So here's where we are now. U of n, because u is going to be based on what n is, which was big X times big T, is going to be that function multiplied by that one. Multiplying those two together, I'm going to call that a of n. And then we have e to the negative k n squared pi squared over L squared t sine of n pi over Lx. Okay. Questions before we keep going? Okay. So at this point, each un of xt, so what we wrote above, is a solution of equation 1 and satisfies those boundary value conditions in 2. Last thing we need to consider is condition 3. Condition 3 was that u of x0 equals f of x. So what we're going to do is we're going to plug 0 in for t up here. When we do that, this whole exponent becomes 0. E to the 0 is 1. So we're left with an sine of n pi over Lx. Okay. So we're not going to be able to find some reasonable f of x to give us this. So what we're going to do instead is we're going to use superposition. By superposition, u of xt will be the sum from n equals 1 to infinity of u of n in this case, that'll be the sum from n equals 1 to infinity of a of n, e, the whole thing we wrote above, how that helps us is if we look at u of x0 now in a similar manner, by changing n from 1 to infinity, we get that f of x to be the sum from n equals 1 to infinity of a of n sine of n pi over Lx. This should look familiar. We also know that x is between 0 and L. Any guesses at all? Where did we see summations like this that involved sines and cosines? Fourier. Now, when we started out Fourier, did we go from 0 to L? We went from negative L to L. What did we call it when we went from 0 to L? Half-range expansion. Yes. So this is a half-range expansion in a sine series. Okay. Basically what we're interested in is finding that a of n. I'm just gonna guess we don't remember how to find that in a half-range expansion for sine. So I could just give us the formula. We good with that? You think you remember?
Yeah.
Okay, do you remember what the coefficient out in front is?
1 over p. There's 2 over p.
It is. In this case, 2 over L.
2 over L.
And we're,
then L to 0 of f of x sine n pi over p, or n pi over Lx. Yeah.
beautiful. Okay, so remember how you guys were like, when are we going to use this? Right now. Okay, we're almost done with this one. Finally, before we had u of xt is a of n e to the negative k n squared pi squared over L squared t sine of n pi over Lx. That's what we had before. This now becomes, now that we know an expression for a of n, this becomes 2 over L summation from n equals 1 to infinity, integral 0 to L of f of x sine of n pi over Lx dx e to the negative k n squared pi squared over L squared t sine of n pi over Lx. Woo!
Is that the, that sounds,
Yeah, that's the answer.
So gross.
I know. Okay, there is a special case of this. Special case is the case where U of x0 equals 100. So the initial temperature throughout is 100. L is equal to pi. What is that telling us? The length of the rod is pi. And then K is 1. If that's the case, A of n becomes 200 over pi 1 minus negative 1 to the n over n. And hence U of xt is going to be 200 over pi, the sum from n equals 1 to infinity of that 1 minus negative 1 to the n over n, e to the negative n squared t sine of nx.
Please, Kevin,
Yes.
we wrote finally the first line underneath that. Should there be the summation sign above the next one in front of AN? Should there be a summation sign there?
No.
Because then where does it come from?
So this,
If there was.
this is where we were before, right here.
Uh-huh.
And then we said we need to find some expression for A of n. So that's when we looked at this condition and we said we're not going to be able to find an f of x.
Okay. Okay. I
Is
get
that
it.
enough? Okay. You guys ready to see what an example of this actually looks like? Yeah? Good, I'm excited. For those of you who like to plan, we have 1.5 more pages of notes.
Is that gonna take a whole period?
My guess would be no. Well, I guess we'll see. Okay, find the temperature. U of xt at any time in a metal rod 50 centimeters long, insulated on the sides, which initially has a uniform temperature of 20 degrees Celsius throughout, and whose ends are maintained at 0 degrees Celsius for all t greater than 0.
Just why didn't insulate on the sides being laterally or on the ends?
Laterally. So that was one of the basic assumptions when we did the heat equation, is we're only going to be solving ones that are not losing or gaining heat of some type. Okay, first thing we want to do is obviously write what the equation and the conditions are going to be. So, starting with the heat equation, it's going to be K times the second partial of U with respect to X is equal to the partial of U with respect to T. We know that K is greater than 0. We know that T is greater than 0. We know that X is between 0 and, in this case, 50. Normally we would write L, but in this case we know what L is. We know that L is 50. We know that there's a uniform temperature of 20 degrees throughout at the beginning. So that tells us that U of x0, when time is 0, at every spot the temperature is 20. And then we also know that the ends are maintained at 0 degrees, so that tells us that U of 0t equals 0 and U of lt equals 0. Again, this is the part that makes the equation homogeneous.
Can you put 50 in there for L, or no?
Yes, I'm sorry, this should be 50. So this is also 50, or sorry, L, rather. What is that 20?
The initial temperature.
What was the notation for it from the f of x? Okay, so our u of xt is going to be 2 over L, the summation n equals 1 to infinity, 0 to L of f of x, sine of n pi over L x dx, times e to the negative k n squared pi squared over L squared t, sine of n pi over L x. So that's what our final solution is going to look like. We are going to start by finding this integral. Yes.
How can it like initially be uniform temp at 20 but the ends are 0?
You just have a round that's one, you just put just like at the end, hold them at 0.
Is it between? It's not
The
less
ends
than or
are
greater.
bad, the ends are
Less
0.
than or greater.
It's just if it's uniform, I would imagine the whole thing would
It's just
20,
less
but
than.
the ends are 0.
Maybe they just mean like uniform.
0 is less than
Same
x,
zero.
less than, not 0 is less than or equal to x.
I don't know. Okay? I don't know. That's just how it is. Just accept it, okay? Ask your physics teacher later today. Okay, so this is going to be the integral from 0 to 50, because L is 50. F of x, like we talked about, is 20. This will be sine of n pi over 50 x dx. So then we're going to be left with 20 times negative 50 over n pi cosine of n pi over 50x from 0 to 50. So this gives us negative 1,000 over n pi. If I plug in 50, I get cosine of n pi minus cosine of 0. I don't like the negative, so I'm gonna switch this around to be cosine of 0 minus cosine of n pi. Cosine of 0 is 1. We've already talked about cosine of n pi is negative 1 to the n. Okay, so our u of xt then, it's going to be 2 over L, so 2 over 50. Summation from n equals 1 to infinity of 1,000 over n pi, 1 minus negative 1 to the n, e to the negative k, n squared pi squared over L squared, which in this case is 2,500, t, sine of n pi over 50x. Not how your answer is going to be written, though. You're going to combine those and the 1,000 over pi, and of course you have to leave. So, final answer is going to be 40 over pi, the sum from n equals 1 to infinity of 1 minus negative 1 to the n over n, and then everything else like it appeared before. It's a constant of some type.
But like the specific heat of the material or something like that.
No idea. Sorry, I would love to be able to tell you, but I don't know. Okay. questions on solving these?
So we're not really even solving them, we're just making it more confusing.
Kind of, yes.
Like, will we have to go through that whole thing that we did today, or just plug in 12?
Like on the test or something where we have to show how we got this equation.
Okay, so here's what I'm okay with. I'm okay with you using that equation if A, you know how I got it, and B, you have it memorized correctly. You do need to know the process though, because you are also gonna see an equation like this in your homework tonight, or a problem like this in your homework tonight. So that part looks the same, but then these are the boundary conditions that you're going to be given. So this is no longer the equation that we started with. So in this case, you're going to have to derive a solution again, like we just did. So if it looks exactly the same as what we started out with, which was this problem here, you can memorize the solution like we found it. Now, when we get to non-homogeneous, there's not going to be a nice solution that you can memorize. When we get to non-homogeneous heat and wave, you're going to have to do this process each time. And that's section 12.6, so that we're starting next week. So you do need to understand it, particularly when you get to this problem in your homework. What do these mean?
The
Ends are insulated. Yeah. Okay, few things to note. First note, this exponent, as n gets pretty big and t gets big, we're gonna end up converging. So ultimately, we don't have to look at a whole lot of terms to get a pretty good representation. This is what people generally do then, and we don't have the power to do this, but this is a 3D graph plotting space and time to find the temperature, using only the first 10 terms. So they decided the first 10 terms were pretty good representation. Sound good? Like I said, we don't have the power